Hello everyone, welcome to this session on teaching AI to learn. Imagine teaching a toddler not just how to speak, but how to speak politely, how to speak truthfully, or how to answer the question in a specific format. We do this by giving a constant feedback to the toddler, like if it is an elder, how to address them, if it is answer this question, how to how to answer this question. That is what we also do with the AI. So in this multi-part series, I'm going to walk you through the different phases of training a large language model. So we start with understanding what is a pre-training. This is where the starting point of your LLM. In pre-training phase is like teaching a kid the vocabulary, the grammar, sentence formation, maybe the knowledge like all the maths, physics, or economics, or history, or the culture. You are teaching lot of knowledge to the kid. This is what the pre-training is all about. In pre-training, the model has been trained on a vast amount of internet data. Like typically, all the LLMs use some data set like Common Crawl, which will have a billions of web pages. So obviously, inherently, the data might have the bias. There may be some racist content, maybe some misinformation, the behavior, the language which we don't want. Then from pre-training, we take the model to a fine tuning. In fine tuning, we do a instruction based fine tuning. This is where we teach the model on how to answer a specific question, or maybe we make the model to be an expert in a specific domain, or maybe a finance domain, or maybe a medical domain, or maybe a economics, right? So it could be anything, or it could be task based, like we find in the model to write a code. Okay, from here on, we move on to a preference-based training. This is where a human feedback is given. If you might have noticed in ChatGPT, every time you ask a question, it gives you thumbs up or thumbs down, or sometimes it gives you two options. It asks you which one you prefer. This is called a reinforcement learning using human feedback. So you, by getting the feedback from the human, the model will evolve. So we are going to see all these things in action. So in the part 1 of this video, we are going to first look into what is model pre-training is all about. So we understand the different steps involved in the model pre-training. Then I'll show you, we take the LLaMA 3.1 8 billion parameters model from Hugging Face. We use a Colab notebook. We load the model. We ask the model a simple question and see what is the response from a pre-training model looks like. Then in the part 2, we do the fine tuning. We fine tune the model on a finance data set. So we want to make the model expert in the personal finance or maybe general finance. So then in the part of the video, by using a framework called Unsloth, we will fine tune the model on a finance data set. In the part 3 of the model is where we apply a preference based training or maybe a reinforcement learning using a technique called DPO. So we'll understand both the techniques like PPO and DPO, and then what are they and what is the difference between them and when to use what, and then we apply a preference based training using the DPO technique. In throughout, we try to compare the model response and before and after. That means after fine tuning, we compare the model response from the pre-training phase and fine tuning phase. And after the preference based training, we compare the model response from the fine tuning phase and then the preference based training phase. So we do this by not just by looking at the response, we use LLM as a judge. So we actually take a DeepSeek model, give the feedback response from both the models to the DeepSeek and ask it to analyze and give its feedback. So by end of this entire series, you would have learned like how basically an LLM goes from ground zero to answering the question. Like this is what basically a ChatGPT or Claude or Gemini might have done. They're done a pre-training, they might have fine-tuned the model, and they done a preference-based training. So that's what happens in entire model training journey, right? But it is good to have knowledge on deep learning. At least you should know like what is a loss function, what is a gradient, what is an optimizer, what is a forward pass, what is a back propagation, and then maybe in transform architecture what is a attention mechanism, and then what are the transformer blocks, what feed forward layer. Knowing all these things will really enhance your understanding of this session. Even if you don't know, I try my best to keep this sessions as intuitively as possible with a lot of analogies and examples, so that you will be able to better understand the core concept behind this. So that's what is going to be the this multi-part session is all about. So now let's understand what is a model pre-training is all about. So let's start with the stage one, which is the model pre-training. This is where we are going to understand how the LLMs are going to learn everything. Okay, so let's get started. So let's begin with first phase in training a large language model, which is nothing but a pre-training phase. So before the model can chat with us or write a code or generate a creative content, it must first understand the structure of the human language. And it does that by learning from a massive amount of raw text, what we call pre-training. So first we feed the model large amount of text data. You can think like a Wikipedia, books or blogs or news article. Basically the entire readable internet we are talking. We are talking like trillions of words. But this raw text can't be used as it is. It goes through a process called tokenization, where sentences are broken into smaller chunks and tokens. So there could be words, subwords, or even individual characters depending upon the tokenization. Then comes the key training task. The model is asked to predict the next word in a sentence again and again across billions of sentences. This is called casual language modeling, and this is the backbone of models like GPT. So even though the model is just you know guessing or writing the next word, it starts from a deep patterns. Basically it knows that there are a lot of patterns in the way the text it is seeing. So it learns the deep patterns like grammar or maybe the facts or maybe reasoning style, even how ideas flow into writing. And it learns all of this without any human label. So no one is telling it's what is right or what is wrong. The model learns by trying, failing and improving. This is called self-supervised learning. We'll see more about this in the next slide. So the basic, essentially to summarize, pre-training is where an LLM builds its core language intuition. It is like teaching the model to read and think before we ever teach it to perform a specific task. Now let's take a moment to understand what are the different types of learnings any AI model can go through. This is, the reason I'm having this is especially important when we talk about large language models like, BERT or GPT. So there are three primary, type of learning a model can do. One is supervised learning, other one is unsupervised learning, and self-supervised learning. So we know about supervised learning from typical machine learning, right? This is what model learn from a labeled data where each input has got a corresponding output. So whether you're using some binary classification or multi-classification, we have the labeled data. Based on that, the model will learn. Next is what? Unsupervised learning, where we don't have any label data. Instead, the model tries to discover the patterns or structures hidden in the data. So a common example could be clustering customer based on their purchase behavior. So you can think of this learning as through exploration. The model is not told what to look for it. This is what we have seen in typical machine learning algorithms. And finally, we have a self-supervised learning, which is the foundation of how large language models are trained. In fact, this is the learning paradigm which has revolutionized the way the AI models are trained, and the modern day what we see, all the LLMs and everything, result of having this self-supervised learning. The trick here is that model doesn't need a label data at all. It generates its own maybe something like a pseudo labels from the raw data and learns by solving the task that it creates for itself. So an example of this is making a word in a sentence and having the model learn to predict the next word. So instead of being taught by something like, assume that you're teaching being taught by a teacher or left entirely unguided, the model becomes its own teacher. It learns by solving a self-generated task using a unlabeled data. So then we can ask why this is important, because self-supervised learning unlocks the ability to train the model using a massive amount of internet data without needing a human label or maybe any type of guiding. So it's powerful and most importantly scalable, and this is what the forms the backbone of modern language models like GPT or BERT, no, or any other LLMs. So before we learn about how the model pre-training happens, what are the different steps involved in model pre-training, we should understand about the two techniques called casual language modeling and masked language modeling. So what is casual language modeling is it is one of the core techniques used in pre-training large language models like GPT. The key idea is very simple. The model learns to predict the next word in a sentence using only the words that came before it. This is often called left to right prediction because the model reads the input sequence from the beginning, moving forward one token at a time, just like how we read a text, right? So there is an example here, right? Let's walk through a simple example. Say for example we have a sentence called language models learn patterns. So during the training we don't feed the full sentence at once. Instead we go by a step by step. So we just start with a BOS token, or which stand for beginning of a sequence token. So the model is trying to predict the first real word, which is language. Now feed the language, the model both BOS and language, and the model tries to predict next word model. Similarly, so that means it keeps on doing like this till it is able to predict the full sentence. Okay, so this step by step prediction is how the models gradually learns language structure from grammar and word order to meaning and context. And remember, the first token BOS is crucial. It acts like a starter marker here, like it telling the model that this is the beginning of the new segment. So assuming if we do same thing, like what are the example I do, if we do this across millions and billions of example, the model develops an intuitive understanding of how language flows and becomes capable of generating the very contextually irrelevant responses. Now let's look at another popular pre-training approach, which is called masked language modeling. This is what used in models like BERT. Okay, so use unlike casual modeling where the model predict the next word using only the previous tokens, the masked language modeling takes a different path. It hides or masks random words in a sentence and tries the model to guess what is missing using context from both the sides. That's why this is called bidirectional context, and this is what made BERT so powerful. So let's walk through a simple example here. So we start a sentence, say the quick brown fox jumps over the lazy dog, right? This was, but instead of feeding the full sentence, we mask few words like this. Then you're having then there is a mask, then there's a brown fox, then there's a mask over the lazy dog. This is like a fill in the blanks. Now the model job is to fill the blanks in this. So using surrounding words, it learns to predict the quick and jumps. Now the model is just looking left to right. It is using the context from both the directions to make the predictions. That's what makes MLM great for tasks like sentence understanding, classification, and maybe sometimes question answering. And the whole approach, just like casual language modeling, is self-supervised. So no human label data is needed. The label comes from the data itself. So we do this by training on billions of such masked sentences. The model learns deep contextual understanding of the the mod language, how words are related, how syntax flows, and how meaning emerges from the structure. So in the next couple of slides, let's understand how the language models are pre-trained. What are the different steps involved? Again, here having the knowledge of transformer to understand what is the tokenization, what is embedding, what is the model weights will help you to understand this better. But assuming that even if you don't know all those things, a model weights are where, to put in very simple language, is where the model knowledge is stored, right? So every time you ask a question like ChatGPT, it is answering the questions, it is correcting something, summarizing. It's all because of the model weights. The model weights is what guides the model, like what next word to predict, based on the question. So for now, assume that the model weights is set of numbers that would represents the knowledge of the model. So in real world there are billions of these models. So for now, to understand that at the very start there is a giant matrices of numbers. So at the very start they're completely random. The model hasn't learned anything yet. It's just like a blank slate. It's just random number. The number doesn't have any meaning. So if you give a sentence like what is the capital of France is, it might give an answer called banana, because it doesn't know anything. It's just doing a random guess. It has no clue. So I'm also trying to give you an analogy of chef here in every slide to compare, to just to keep it more intuitive. So think of it like, imagine a brand new chef who just entered the kitchen for the first time. He has got a blank recipe book, no instructions, no tips, no experience. When someone says make a pasta, he just guesses. He might make a chocolate sauce, or maybe he might add some chocolate and noodles, not just because it's creative, but because he doesn't know any better. That's exactly how a model behaves with the random weights. It is trying to cook without knowledge. So to summarize, at this point, the model is full of random potential. To summarize, for now you assume that the model knowledge is what the model weights represents. Everything you get a response from an LLM because of that model weights, and those model weights are the one which guides a model with the response, and those weights are random at the beginning. Okay, so now that we have initialized the model weights, let's look at what happens when we feed some text. So from here on, we are feeding one text to the model and asking the model to predict the next word. So here, say we have a phrase called I love pizza. Okay, the model doesn't understand words directly. It first converts them into number using a process called tokenizations. So each word or part of the word is mapped to an unique ID. I becomes say 101, love becomes 2000, pizza becomes 3000. So these tokens are numerical inputs. Remember, the models understand only numbers. So everything you see in the model, nothing but it is converting into tokenization. In fact, I made another video on tokenization to explain what the tokenization process is all about. You can watch that video to understand what is a tokenization. In fact, you can see a real world example of building a tokenization from scratch. So these tokens are now the numerical inputs. They pass it through the model layer where the random weights process them to generate a predictions. So on the just to give you some same analogy on the right side, in the chef analogy. So imagine the chef receives a written request, make pasta. But remember, the chef is still new, so he has no standard recipe yet. He reads a note, maybe scratches his head and look at his nearly empty pantry. So he's trying to interpret the request and make something using only instinct and what is available. That's exactly what model is doing. So taking this input, the input prompt, and trying to process it with current untrained weights. So in this step, the model is converting human language into the numbers, which is machine readable tokens. But these tokens only become meaningful when the model has learned the patterns in the weight. At this stage, it is just guessing widely, just like our chef who doesn't have any clue on how to make the pasta. Now let's also, before we go to the next step, we'll also map this to a real world. So in real world, like web pages or articles actually gets fed into large language model during the training. So this whole process starts with a raw internet text. This can be anything from a news article to a blog post to code, Wikipedia pages, or some forums or product reviews. At this stage, the content may still contain a lot of noise like HTML tags, navigation bar, emojis, irrelevant metadata, right? Next, the system cleans this raw content. It removes non-text elements, filter out junk, and extract the meaningful textual content, the actual paragraph, the sentences, and lists that make up a human language. Then comes a crucial step called chunking and tokenization. Here, the clean text split into fixed size blocks, often around say 2048 tokens per chunk. So they aren't neatly aligned to paragraph or sentence. They are raw text segment that fits into the model input window. So each chunk is then tokenized, meaning every word or subword is converted into a numerical ID. So for example, if we take the word called transformers change, NLP might become say number called 299448112 and 3094. Now we are ready to pass this data through the model. So these token chunks are fed into transform model layer by layer and one by one. So during training, the model doesn't see the full document or even a paragraph. It only sees window of tokens and is tasked with predicting the next token at every step. So, so this is how the pre-training works in a practice. LLM don't read full pages and reason or entire paragraph at once. Instead, they learn by sliding over billions of short tokenized chunks of internet data. So one sequence at a time. So over time, they internalize the structure, the patterns, and the meaning of the language. Now we'll see what happens. We fed one word to the our training, and let's see what happens the next. So now we have taken a so far we have big giant matrices of weights, which is also models knowledge. We have initially the random numbers, and we have taken a sentence called I love pizza, and then we have tokenized that is converting that words into the numerical format which the model can understand. Now in the forward pass, this is where the training comes. We give the model I love. Now it has to predict the next word pizza, right? This is what the training is all about. So now it receives a word called I love in this case. So it runs its input through its network using the current weights. So these weights determine how the model processes the input and what it thinks comes next. But remember, as I told again in the previous slide, the model hasn't been trained yet. It is just weights are still random. So instead of completing the sentence with something sensible like pizza, it might predict something totally off, something like a dogs. Technically, the model is doing what it's supposed to do. It is making the prediction of the next word, but it's not a good one yet, right? So it is doing its job. When I say I love, even though I love pizza is the input, so you give I love, you are supposed to get I love pizza. Now it is giving I love dog. That is the wrong. It is making a mistake because the weights, the knowledge it is having is random. So you compare this with our chef example. He get a prompt like he get a ask like make a pasta and try to follow some rough ideas. He hasn't practiced it yet. He doesn't have a refined recipe yet. So instead of pasta, he might serving a burger with a confused maybe expression on his face. So he followed something, but the result wasn't what the customer wants. So same thing with model. The output is based on what the weight currently tell it to do. Right now, those weights are guessing. So this step is called forward pass, is where the model makes a prediction using what is known so far. Just like our chef is going to get wrong a lot in the beginning, this model also going to get wrong in the beginning. So that's okay because the next step is where we evaluate the output and start to improve. So in the previous step, our model made a prediction. When you give I love instead of pizza, it gave the word called dog. So this is where the next part is about seeing like how much, what is a mistake it has done. So mathematically we have something called loss function, which is nothing but how much of error the model has made in the prediction. Like it compares what is a predicted minus the loss. Maybe something like a mean square error, something like you are having a typical deep learning neural net where if you are having y hat is prediction, y is your actual, so y hat minus y whole square, right? This is what the loss function. I'm trying to keep it very intuitively, so not even if you don't know the deep learning, just to want you to understand what the loss function is all about. So once a model makes a prediction, the next step is to evaluate how good or how bad the prediction was. In this example, the model predicted the next word would be dogs, but the correct word is pizza. So how do we measure how wrong prediction was? This is where the loss function comes in. So the loss function compares the predicted output with the expected one and gives us a numeric score. In this case, the loss is 2.5, which means the prediction wasn't just wrong, it is quite far off. The higher the loss, more of the target model. So maybe I just also want to add some technical details here. So typically, even if you take any neural network, the loss function is the first. Once after the forward pass is over, the first thing is that you compute the loss gives us an idea how far your prediction has gone wrong. Just to compare now with your chef example, so he just cooked what he thought was a pasta, but remember he just made a burger instead of pasta. So he still doesn't really know what he's doing. So he tastes a dish and immediately realizes this isn't a pasta. So maybe he gives himself a score of 2 out of 10 and even writes this is not a pasta. This is what exactly loss function does. So it will basically doing a taste test. It tells us how far the output from what it should have been. So the loss function is very critical. The reason being it signals the model, maybe it guides a model into the learning. If the loss is very low, we are close. So whole idea of all our training is to minimize this loss. So if the loss is high, we have got a lot of corrections to make. This is where the next step we call back propagation comes in. To summarize to what we have done so far, we have initialized the weights in the step 1. In step 2, we have taken a sentence called I love pizza. We tokenize that sentence, converting the words into numbers and pass those numbers to the model. Now using that model, the model, that it goes to the same, network layer, all the layers in the neural network. It is predicting what is the next word. The next word came out to be dog, and which is wrong. Now we computed the loss. Again, this is going through all your typical transformer blocks where it is first going through the attention mechanism, it is going to the feed forward layer and everything, and now you're having the output. Now once a model has made a prediction and we have calculated how wrong it was using the loss function, the next step is to figure out why it went wrong. So this process is called back propagation. The idea is to trace the error backwards through the network and ask which weight contributed the most to this mistake. So for example, typically you have an input layer, you might have a couple of hidden layers and an output layer. So what you're trying to do is now on the output layer you got some error, you found the loss. Now you have to go back in each layer and then ask a question whether how much of this this weight contributed to this error. So mathematically this is what we called a gradient. So basically what is gradient, again mathematically explaining, this is a partial derivative of the loss function with respect to each weight. So if we have the loss function, say say y hat minus y whole square, and then you are having say weight w1 w2 w3, now you do the partial derivative of this loss function with respect to this weight to understand how much of this particular weight has contributed to this particular loss. So this tells the model, hey, this weight made things worse, reduce it. or maybe it says this weight helped either keep it or maybe slightly increase it. So it is like asking how much did each part of the model affects the final error. Now compare, go back to our chef example again. So he just gave a 2 out of 10 rating for his previous dish. So he traces back his steps. Did I use too much garlic? Did I boil the wrong noodles? Did I mess up the sauce? So he marks issues directly on the recipe. Hey, too much garlic, wrong noodles. This intuition is behind the back propagation. It is just like you were writing some code, you got some error in the output, you go back and check. So in the full layer, whether I got some error in the UI layer or maybe error I got in the middle, in my, the backend layer, or maybe some error in the database table. So you go back in each layer and check where exactly you went wrong and how much you went wrong. So this is what intuitively the back propagation means. So the back propagation means taking the loss and trying to understand how much of each model weight contributed to this particular loss. So mathematically in the model you are trying to compute the gradient, which is nothing but the partial derivative of the loss with respect to each weight. So it doesn't, but remember one thing, it doesn't fix the model yet. It is just telling you where and how to adjust. It gives us a gradient, the signal we need to nudge the weight in better direction. Sometimes it is some given example is giving direction there what direction you have to change. So for example, I know you are trying to reach a goal and maybe you made some wrong steps in the wrong direction. The gradient telling like whether what direction you need to make the corrections. So the actual update comes in the next steps. So far we know the loss, that we loss means we know the mistake, and we have identified in my whole network which weight in each layer contributed for this particular loss by doing the partial derivative of the loss function with respect to that particular weight. Then the next step we are going to fix that particular error we have made. So far we have initialized the model, we have given an input, tokenized input, ran through that, it made a prediction called I love dog instead of pizza. We computed the loss, and then we also computed the gradient in the back propagation, which tells us how much each of the model weight contributed for this mistake. Now it has come to time to fix that error. So now that we know the gradient through the back propagation, we need a way to apply this gradient to actually improve the model. This is where the optimizer comes in. So think of optimizer as a model, a tuning tool. It uses a gradient value to decide how much to adjust each weight. So there are many types of optimizer like SGD, Adam, RMS prop, but the job is same. Take the gradient and make a tiny changes to the weight to reduce the future loss. Here the signals, you can see the optimizer is feeding through the error signal back into the model and adjusting the number in the weight matrix. So each training step makes a small update, maybe 0.001 or even smaller, but those add up across millions of steps. So again, coming back to our chef, who still did a mistake. Now he realized what mistake he has done. So imagine he tasted the dish. Now he knows that yeah, them salt is missing in this dish. So he's tried to add a little salt again, and maybe little bit of garlic, maybe some chili powder he start making. He made some tiny tweaks guided by the earlier feedback. So he doesn't start from scratch. He keeps that what worked and adjusts what didn't. That's what exactly the optimizer does. It refines the model weight so the next prediction is little closer to the target. So this is the heart of the training. Back propagation tells us what went wrong. The optimizer tells us how to fix it, and the model get updated and the model improves. Over time, this cycle repeats until the model becomes a matured enough to predict the words correctly, or our chef becomes a seasoned chef. right? That is what the next step is going. So far, we have seen the model going through a single training cycle. It got the input sequence, it made the prediction, it measured how wrong it was, it computed the gradient, it updated the weights. But a single example like I love pizza isn't enough to teach language model how to speak. Now this process need to be repeated millions or even billions of times using a diverse real world text. That's what all these models will go through. It takes a text from news articles to Reddit comments to Wikipedia pages to books. Each of these examples get tokenized into numbers, fed into models, and used to refine the weights one tiny step at a time. Imagine the amount of the computing power required. That's why the training in LLM is very expensive. It requires a lot of huge amount of GPUs. It's a millions and $1 billion of investment required to train these models, right? Because you need to first have that, crawl the data from all the web. You need to clean the data, pick up the meaningful data, and then train this model again millions and billions of times before you actually arrive at a large language model which can actually predict the next word. That's what happened. Just like our chef, he might made only one dish, but he wouldn't learn much. But imagine he's cooking every day, meal after meal, day after day, like 365 days he's doing without taking a single break. He's doing from morning to evening, cooking continuously and then tasting, adjusting, testing, adjusting. Maybe by end of some time, like year, he becomes one of the best chef in the world, which can cook any type of dish. So that's what the large language models does. They keep on training the models, and every, like, you take sentences, paragraphs, you keep predicting the next sentence, next word by different word paragraphs. It just not only becomes a predict in the expert made next word, it also learn the patterns in the data. So this is what the training model is about. Not just about memorizing individual phases, it is about learning the patterns from sheer repetition. Just like a chef builds intuition over thousands of dishes, the model builds a fluency by refining its weights across billions of text examples. The repetition is what gradually turns random weights into a perfect language model. Now, after millions and even billions of training steps, something amazing happened. The models is changing drastically. It becoming prediction becomes more accurate. The loss of score, how wrong it is gradually going down and stabilizes. So we call this state convergence. It means the model has effectively learned from the data. At this point, the weight inside the neural network represents a rich understanding of the language, the facts, the reasoning patterns. It can now generalize a brand new text it has never seen before and still respond correctly. Okay, again going back to our chef. Now he has practiced thousands of dishes, refining his techniques. He no longer second guess himself. He knows which ingredients work together, how long to cook each dish, and what adjustments to make without thinking twice. So that intuition, just like a chef develops in making dishes, the language models learn the same intuition on the language, right? So to summarize, and this is what the model achieves: from a random guess at the beginning to a confident intelligent response at the end. Now it is this is where the pre-training phase comes to end, but at this point it is not perfect, right? It can predict the model, the next words, it learned pretty much all the text in the internet, and it can uh, answer you a lot of questions but not in the way you want. That's what we'll see in actual demo. We'll take a llama 8 billion parameter model which is not fine tuned, which is a pre-trained model, and then see like what response it gives and see like what corrections we can make again in that model during the fine tuning phase. So this is the model we'll be using in remainder of this, both for the pre-training and then for the preference-based training, and then sorry, fine-tuning and preference-based training. This is already a pre-trained model. That means this model has been trained on all the publicly available online data, and there's a cutoff time. I think this model has been trained till 2023. Okay, so and this is some of the transformers how you can execute this model, and then you can see some of the training time you can see is huge, 13.3 million GPU hours. That means this model might require a cluster of GPUs for a month together before this has been trained. That is the amount of investment required to train a large language models. There are also model benchmarks. I plan to have another separate video where we'll walk through different benchmarks in the model, different parameters and what they actually mean. It's separate session altogether. We don't have time for that today. And then you can go to the next tab here where you can see the files and versions. To start with, you can see the config.json. This will give you some whole idea about the what is the model architecture, and you can see that number of attention head is 32, number of hidden layers 32, and then the boss token ID. We discussed about the boss token in the previous in the slide, right? That is beginning of the sequence token, and what is the token ID for that. So, and also it has got some generate config. These are the default parameters used, like temperature 0.6, 0.9. These two are key parameters. They tell, like temperature tell how creative the model has to be. Like if you have higher temperature, the output from model is going to be different every time. But if you want a very predictable output, you could make a low temperature. Top E tells what is the cumulative probability of the tokens which it has to take. Like if it is a 0.9, that cumulative probability of the tokens is 90%. After that, it stops. It takes only the tokens with the cumulative probability of 0.9, right? So that's about the other configs. If you can go back again, these are all the model weights. In fact, you can open one of them. You can actually see that these are all the QKV projection weight model weighters. You can see that this particular matrix is having 400,000 parameters, which is a 0.17%. Like this, in every layer what they're having, you can see the model dimension, the matrix dimension also. This is having almost like a 5 million parameters close to. So like this, you will have multiple of these tensor files, and this is a index file which tells you like which file is having which model. Like you can see that, for example, model layer 1, down projection, gate projection, projection attention layer weight is there in this file. Okay, this is a time of index file for all the layers of the model. And then yeah, this is the model tokenizer. Okay, this file is too long. This is a model vocabulary. In fact, you can download this file and then check that file. And then if you can go back again, this is about tokenizer config.json. This is about the tokenizer configuration for the tokenizer. Yeah, this is about the model. This is a pre-trained model. Now what we'll do is we'll load this pre-trained model in the Collab notebook. We'll give it a simple input and see how it behaves. Okay, and then in the next, after this session, in the next session we are going to fine tune the same model. Start looking at the Collab notebook. Here I'm having Collab notebook where we are going to first load the model and the pre-trained model and see how it works. It is good to have a GPUs because you will get more computing power and the models loading will be faster. With the CPU, 8 billion parameter model like Llama might be a little bit slow to load. So you need to have and also you need to have Hugging Face login token. So once you have the token, you just do it. Since I already logged in, it doesn't show me the pop-up me the token. Otherwise, you need to do a login, have Hugging Face token. Now I'm installing these three libraries. I'm going to explain what they are. So before we start, we need to first understand a concept called quantization. Of course, it's very, I've tried to make it very simple here instead of going to lot more detail, just so that we can proceed with this loading the model. So typically, large AI models uses billions and parameters, parameters, right? So what is means is that these models use billions of numbers to represent that knowledge. These numbers could usually take 16 or 32 bit. So that makes them very huge and expensive to run. So what is this quantization is that this quantization shrink these numbers into smaller precision, like using either 8-bit or even 4-bit, while keeping the models, the smart, the parameters mostly intact. So why it matters is that this makes model faster, lighter and cheaper to run. This think like, if you want to store in a high resolution photo, right, you don't always need to store in a raw format. You can store in a compressed JPEG format, still look nearly the same, but you just far less, space. So but it doesn't mean that the model is going to decrease the precision and something like that. So the way it works is that, say you have original weights like say minus 2.4, 1.7, 0.2, 1.3, 2.6. What it does is, in quantization, it creates a sort of a lookup table for the range. So what it does is, typically, suppose the range is -3 to +3, with 4 bits you have 16 levels. So each bucket could have a width of, say, approximately 0.4. Then it maps each float value to the nearest bucket. So for example, -2.4 is mapped to say -2.2, nearest one. So -2.2 is there in the index 2, right? So instead of -2.4, it stores the index 2 in a quantize. So say -1.7 is closer to -1.8. So that is in the index 3. So it stores index number 3 for the -1.7. Now it is shown in 4-bit. So when it wants to go back again to the original model, it will dequantize. That means now it knows that the weight for this is in lookup, index number 2, index number 2 -2.2 is there. So but obviously this might reduce the precision little bit, but not with without greater impact. Now again, every model has got its own tokenizer. So you try to load the tokenizer here first, and we use bits and byte config to load the quantization. For example, here I'm trying to load the model I'm doing a 4-bit quantization. Now we are having a tokenizer. So every model will have its own tokenizer. Tokenizer is the model vocabulary. So now with this, we using auto model for casual LM library. We are going to load the pre-trained model with pass model ID. Again, device map is equal to auto means it automatically assigns a model layer to all available GPUs. And then once we load that, of course it takes some time. So already load the model. It usually takes 4 to 5 minutes to load all this model files, because these are the files we saw, right? When we saw the model talk, it is localizer config.json. It has to load all this. It has to load all the safe tensors, which is almost like each one is, you can see, like 5 GB to 4 GB, right? So it has to load all these files. So now it has loaded all these models into the memory. Now let's give some simple inputs is model. We ask question and answers and see what inputs. Actually, now we can run this, but I only ran this examples. For example, if I pass this question, it gave me this response. See, that's what it is. This is a pre-trained model. It is able to give the response, but it is not perfect. It is not in a chat-based style. It is not actually giving you the response in a format you want, or maybe it is not giving you very focused answers. That's what the purpose of fine tuning is all about. So now if you see, the pre-trained model is like a rough model, like it knows all the knowledge vocabulary, but it is not specialized in something. It doesn't know how to give the answers in a specific format. So that's what we are going to do next. We are going to look into the model and then fine tune this model on a specific finance data set, so that it can answer in a specific format you want. So that is what going to be the focus of next session, and I'll see you again in the next session on fine tuning this model. See you then.